Good afternoon. Welcome back. This is the tea time speech. It's actually the final one of our series. And it's going to be, I'm sure, as interesting as the others. So we are lucky enough because we have another excellent speaker. We have Professor Elias Combarro. Oh my God, I got stuck. I'm sorry, Elias. Okay, we are live, so that's the way it is. And he's going to tell us why and how you can detect the fact that not all of the random number generators were born equal. So thank you for your time. Thank you for dedicating your precious time to us. The floor is yours, Elias.
Thank you very much. Well, first of all, I would like to thank the organizers of the hackathon for inviting me to give this talk, especially Professor Massimo Caccia. It's a pleasure for me to be here. And first of all, I would also like to wish luck to all the teams. I know they are working hard, and I wish them all and every success. Let me share my screen for a moment. Okay. Can you see it?
Yes, we can. Okay. Very clear.
So as Professor Caccia has mentioned, this talk is about the difference in the random number generators that you can use and how they can influence the performance of your applications. I'm an associate professor at the University of Oviedo in Spain at the Computer Science Department. And since July, I'm visiting CERN, particularly CERN Open Lab, and I'm collaborating in a project in which we are studying how the quality of random numbers, especially random numbers generated with quantum devices, can affect processes related to high energy physics. So I'm going to tell you a little bit about how your applications can suffer some loss in performance if you don't choose the correct random number generator. Well, as you've already heard in many of the talks so far, and as you know, because you are working on applications that use randomness, randomness is very important in many different fields. Of course, it's central in cryptography. We had a very nice talk this morning on the relationship between cryptography and randomness. And you know that even if your random number generator is a little bit off, it has a little bias, this can influence the security of your applications when you are using this random number generator. Also, randomness is used extensively in different kinds of simulations, in statistical simulations, in Monte Carlo simulations. This is the particular field in which I'm working at CERN Open Lab. And you will see, I will show examples in which if you choose a bad or an inadequate random number generator, your results in these simulations can be incorrect. Also, another field which needs a lot of randomness is machine learning. When you train a model, you need to initialize the values of your model. You need to sometimes shuffle the data that you provide to your model. And this is done in a random way. So if you have a random number generator that is not adequate, this can impact the learning process that you are trying to develop. Also, of course, randomness is also central in games and lotteries. And here you want your process to be perfectly random, because if there is some deviation, if there is some bias, people can profit from these deviations and somehow hack your game or your lottery, and this is something that is, of course, not desirable. And well, all these applications and many others are more and more demanding a lot of randomness, and especially good and high quality random number generators. So how to select these random number generators? I remember when I was a student and I was learning, for instance, about algorithms like quicksort, that the textbooks always mention, well, you need to select this element or the other in a random way. And then that was it. They were straight to explaining what happens after you select this element. But when you wanted to implement this, you had no clue, no advice on how to select the random number generator. And it happens that sometimes the default random number generators of your favorite programming language, may it be Java or Python or C++ or whatever, are not as good as they should. And the impact on your applications can be bad, okay? So there are different figures of merit or different factors that can make a random number generator different from others. Of course, there are random number generators which are more efficient, and this is something that you always want. You want more random numbers in the same time. But at the same time, there are random number generators that are more uniform, more random than others. And we will see examples of these behaviors. And for the applications we have been mentioning, especially cryptography, simulations, gambling, and lotteries, you want a random number generator that generates bits, that generates numbers as uniform as possible, because any deviation can be bad for your results. And I will show you how historically some flaws, some defects on the random number generators that people use for different tasks have led to disasters, to some catastrophes in some applications. So then the question is, well, I need to choose a random number generator for my application. How can I evaluate it? How can I be sure that this is exactly what I need, that this meets all the criteria that I need for my application to be successful? This has already been mentioned in some of the talks, but let me remind you that there are suites of statistical tests to see whether the output from a random number generator is sufficiently uniform, sufficiently random or not. You have, for instance, the famous NIST suite, the Die Hard and Die Harder, several different suites that you can find online, that you can download, that you can run with your favorite random number generator. And what happens is that these suites perform a statistical test on your strings, on the output of your random number generator. What they do, in fact, is to assume that the string that you are providing comes from a uniform distribution. And under that assumption, they test or they compute the probability of obtaining exactly that string. And then they compute this probability and compare them to a given threshold. And if the probability is below this threshold, then the test is not passed. For instance, the most famous or the most simple of these tests is you have a string of zeros and ones. You count the number of zeros, you count the number of ones. And if the string comes from a uniform distribution, you know that the number of zeros should follow a binomial law. And you can compute exactly what is the probability of obtaining a string with that number of zeros. If the number of zeros is too low or too high, then the probability goes exponentially fast to zero, and you can check, or you can you have a proof that this string is very unlikely to have come from a uniform distribution. This is something that was discussed also this morning. With this test, what you can check is that your random number generator has some problems because it is not compatible with the hypothesis that the strings come from a uniform distribution. But sometimes these tests are not enough, because there are some pathological cases in which this test can be passed, by some by some random number generators or by some processes that produce strings of zeros and ones that we wouldn't consider random at all. For instance, here I'm showing a table in which several of the tests included in the NIST suit are passed when we take the first 1 million digits of pi. And we consider this as coming from a random number generator. We feed this into the NIST test, and it can be checked that most of the tests are passed. This is something that has been repeated, for instance, by Marsaglia and other people, also with other numbers, with rational and irrational numbers. And in most cases, you obtain sequences that pass many of these tests or most of these tests. And by any reasonable definition of randomness, I think we wouldn't consider this to be random. In fact, nobody would use the numbers, the digits in pi, for instance, to generate keys in a cryptographical system, because of course this is not random at all. Okay, so what else do you need to know about a random number generator in order to evaluate whether it is suitable for your application or not? Well, you should know something about the process that is involved in the generation of these random numbers. From this point of view, we can classify random number generators in two different families. We have the pseudo-random number generators, and we have the true random number generators. The pseudo-random number generators are those generators that in fact implement a deterministic algorithm and usually depend on a seed. But whenever you run these generators with the same seed, you obtain exactly the same numbers. So of course, this is a deterministic process. This is not random, but it's something that is similar to random in the sequence that you obtain from the seed. So if you run these pseudo-random number generators with these test suits, they pass many of these tests included in the suits. But by any definition, again, these are not really random, they are deterministic. What we can consider as an alternative way of generating random numbers are true random number generators that use some physical process. Some examples have been mentioned already in previous talks, maybe thermal noise, atmospheric noise, and of course, quantum systems, which is the way in which the random number generators from random power work. In this case, you can use the entropy of these systems to obtain true random numbers. Okay, so this is something that you need to consider, that pseudo-random number generators are really not random, but deterministic. Anyway, historically, pseudo-random number generators have been very important. Even John von Neumann was the inventor, as we will see later, of one of these, or one of the first pseudo-random number generators. And he was well aware that this was really not a perfect way of generating randomness. So in order to study what can be the problems when you use pseudo-random number generators in your applications, it's good to know what is the general structure of one of these generators. So to define a pseudo-random number generator, we have several elements. We have an internal state that at the very beginning is initialized from some seed. And then we have both a transformation function and an output function. The transformation function is applied each time a new number is needed from the generator, and it changes the internal state. And then from that internal state, there is an output function, which can be the identity, that returns a new random number that can be used for your application. So this is something that depends on the definition of this transformation function, on the way in which you obtain random bits from your state, and also on the seed. And this will be very important in the following examples to see how this can fail in several different ways. So I mentioned that John von Neumann, although was aware that generating random numbers with deterministic processes were not the best way, was the inventor of one of the first methods to generate random numbers with computers. And this is a historically interesting pseudo-random number generator, although it is really not very good. We will see that it has very poor properties. So the idea of this method, which is called the middle square method, is to take one state, which is an integer value, to square this value, and then take the middle digits of the result as the new state and also as the output of the random number generator. And if we study this generator, we can see, at least when we have here just two-digit numbers, that the behavior is really not very random. For instance, well, I don't know if you can see because some of the numbers are really tiny, but if you start with 50 and you square 50, you obtain 2,500. And if you take the middle digits of that number, it's again 50. So you are in an endless cycle. It's not random at all. And for the rest of the values, you see that after some steps, you either enter a cycle or you go to one number, which is like a value that is always the same, even when you iterate. So this is really not a very good example of a process that can generate random numbers. And even if you increase the size of the states, you obtain similar behaviors. So an improvement over this proposal was defined some years later, and it's what we call linear congruential generators. In this case, again, we use arithmetical processes to generate random numbers. We start with an initial state, and we multiplied subsequently that number. We obtain that number times a constant a, and we add also another constant c, and we take the mod, the remainder of the division by m as the new state, okay? So this is a pseudo-random number generator that has been used extensively since its definition in the 60s. But the properties of this kind of pseudo-random number generators depend heavily on the choices of the values a, c, and m. There are several different mathematical results that relate the choice of these parameters with for instance, the period of this generator, because it's easy to see that once that you obtain one value that you have already seen, the rest of the process will repeat endlessly in the same period, okay? So you want your pseudo-random number generator to have a long period. And for instance, if you take m, the number by which you are dividing the states to obtain the remainder, if you take m as a prime, you can show that then the period is maximum. Okay, and the maximum period in this case is m, because that is the different values that you can have from 0 to m minus 1. Okay, so you need to be careful about how you choose these values. And unfortunately, historically, there have been some very bad choices of these values. For instance, there is this famous instance of the linear congruential generators, which is called RANDU, which was very popular in the 60s, which has this expression here. You can see that the mod is a power of 2, and this is a natural choice because division by powers of 2 can be performed very quickly on digital computers. And this other number is just 2 to the 16 plus 3. So this is again another operation that you can perform very quickly on digital computers. And this was one of the reasons why these values were chosen, and this linear congruential generator was used extensively in the 60s. But if you just compute what happens after you apply this generator on the state 2 times, you can see that since this number is 2 to the 16 plus 3, when you apply it twice, you obtain several factors. One of them is 2 to the 32, but 2 to the 32 mod 2 to the 31 is 0. So what you obtain after 2 steps is this number, which is in a linear relation with the 2 previous ones. So although if you take a look only at the individual values and you put them in a line, the statistics can be close to uniform. If you consider 3 of these values and you draw them in 3D, you obtain that all of them lie in these planes. And of course, this is not random at all. And this comes from the bad choice that was made for this linear congruential generator. So this is something that should be taken into account. Another problem that has been noted in the use of pseudo-random number generators is that for several different applications, for instance, Monte Carlo simulations, some pseudo-random number generators that were considered good offer incorrect results. So I'm not going to explain in detail what the Icing model is. This is one of the models we are working with at CERN openlab to test the quality of pseudo and quantum random number generators. But the idea here is that you want to sample some configurations from a model of the different configurations that you can have in a physical system obeying a certain Hamiltonian. And for that, you use something that is called the Wolf algorithm. The Wolf algorithm is a Monte Carlo method that allows you to sample possible configurations of the system when you have a certain temperature. And this Monte Carlo simulation, as all Monte Carlo methods, need to make some random decisions. So you need to select the initial configuration, then you select one of the positions in the grid at random, and then you expand this position with several of the neighbors, and with some probability you add them to the cluster or not, and then you flip them. Okay, so it can be shown mathematically that if you select this completely at random and following the adequate probability distribution, what you obtain is exactly what you would obtain from a system obeying this Hamiltonian. However, in 1992, Fehrenberg, Landau, and Wong were testing the use of this Icing model with what is called a lagged Fibonacci generator. A lagged Fibonacci generator is similar to a congruential generator in which, in the sense that the values are obtained from the previous one by making some arithmetical operation on previous values and then taking the remainder by m. But here what you have is that instead of considering the previous state, you consider states that may be five steps back or 7 steps back or whatever. Okay, so that is the difference of these generators with the linear congruential generators. And they were trying these pseudo-random number generators with different operations, and they noticed that for some choices of the operations, in particular for addition and subtraction and the XOR operation, the results that they were getting were nowhere near what they should obtain. In the case of the 2D Icing model, you can analytically solve the system and obtain exactly the values for the energy, the specific heat of the configurations under this Hamiltonian. And here we can see that, for instance, using this generator R250, which is a lagged Fibonacci generator, the difference between the value that you should obtain and the correct value were more than 40 sigma apart. And also for the specific heat, they were more than 100 sigmas apart. This also happened with this SWC, which is a subtract with carry generator, which is a lagged Fibonacci generator in which you use the subtraction. And you can see here that again, we have a very big difference between the correct value and the value that you were obtaining with this simulation. And this shows that there is something not really random, not really uniform about these generators, because you can mathematically prove that if your distribution is completely random, then you obtain something that is close to the correct value.
Elias, can I disturb you for a second? So
sure.
For my own curiosity, this is very interesting to me as a physicist. So a question is, if you run any of the method that you have been using and shown to be wrong in the Icing model across, for instance, the NIST suite, what do you get? So the essence of the question is, maybe you need actually to test the reliability and the randomness of your generator using physical situations where you compare the numerical solutions against the exact solution, which is very different with respect to pure statistical tests.
Yes, you are completely right. And in fact, some authors have suggested including this kind of tests also in these suits. The problem is that the problem with these tests is that they are computationally expensive.
Okay.
Usually the NIST tests are much easier to run. For instance, you count the number of zeros, the number of ones, or you divide your stream in different chunks, and you do some easy computation. But here you need to run this model for some time, and depending on the size of the grid, it can be computationally expensive.
Okay. Yeah.
But
okay.
You are right. Some people have suggested to use this as an additional test for randomness.
Yeah.
So, well, this is not an isolated case. For instance, in 2004, it was discovered that another kind of pseudo-random number generator, which is called the linear feedback shift register generator, were also obtaining incorrect results. For instance, when you generated long sequences of zeros and ones, if the generator is completely uniform, the number of zeros should follow a binomial distribution. And well, I don't know if you can see here this gray line, but in some cases that Bauke and Mertens were testing, the number of zeros were very different from the ones expected from a uniform distribution. This has also happened in other domains, for instance, in simulations of organical and biological systems. Here you can see that a linear congruential generator is giving again incorrect results. Also in molecular simulations, here we see again Randu, we see in blue a linear congruential generator, again incorrect results. So this is something that is, it has been noted several times. So even if you are using a famous or a popular simulator, and some of these linear congruential generators, for instance, were the default choice in some programming languages for some time, you can obtain very bad results in your applications. Other problems that can happen with pseudo-random number generators include the difficulty of setting the initial state. As we have seen, the initial state depends on an external value that we call a seed. And if you provide the same seed, you obtain the same number. So this seed should be random somehow. This is kind of a problem if you are trying to obtain randomness, because you need some randomness at the beginning, but this seed usually is much smaller than the string that you obtain later. So from a short random string, you can obtain a much bigger string. That's the idea with the pseudo-random number generators. But this seed should be very random, should have a lot of entropy. There was this famous problem with the Debian Linux distribution in the year 2006, because some developer noted that one of the tests he was conducting on the code for the OpenSSL package was showing a potential bug because a variable was being used before being initialized. But this was a clever trick that was used by the OpenSSL developers to obtain randomness. So this person commented out this line and then reduced it dramatically, the randomness of the seed. In fact, it reduced it to only 15 bits. And it was possible to crack all the different keys that were being generated with this OpenSSL package, because there were really very few seeds to try. Okay, so this affected other systems. This affected, for instance, Ubuntu, that you know is based on Debian. And here is a funny cartoon by the people at XKCD, which is a favorite of mine, in which they show how
every nerd loves XKCD.
Of course. And it shows how if you comment the incorrect line, you can have very, very bad behavior in your systems. Also, something similar happened with Netscape. Maybe the young people that are participating in the hackathon don't know about Netscape, but this was a very popular browser back in the 90s, the late 90s, and probably the early 2000s. And in this case, the seed was obtained only from 3 values: from the time of the system, the ID of the process, and the ID of the parent of the process. And it was very easy to guess these values and to obtain the seed, and from that to break all the security of this browser. Another which is closer in time and which is a favorite of mine was this problem with the Rsa Cryptosystem. This is a cryptosystem that is used widely in many different applications and online systems. And as you know, it's based on the difficulty of factoring a number which is the product of 2 primes when this number is very big. But this can be much easier to break if there are some coincidences in the primes that constitute 2 different keys. So ideally, you generate these prime these prime numbers that form the key or part of the public key completely at random. And it shouldn't be possible, or it would be very unlikely that 2 different keys have one of these factors in common. But it was discovered by some researchers in 2012 that out of 10 million keys, almost 30,000 shared a common factor. And if they shared a common factor, then factoring them is very easy, because you only need to apply the algorithm for the Euclid algorithm for the greatest common divisor. Okay, well, I had here a slide to show you how this works, but I think it's clear and I don't want to spend too much time. Other famous security problems caused by a not very good design of the pseudo-random number generator, or by problems with the seeds, or other design problems, include, for instance, the pseudo-random number generator that was included in Windows 2000 and XP. In this case, this algorithm was not published. It was not public. And this goes against one very important principle in modern cryptography, which is called Kirchhoff's principle, that all your algorithms should be public, so they can be studied by experts, and then if there is any flaw in them, it can be discovered. Well, this was not the case with Windows XP. And in 2007, some researchers found that there were problems with the pseudo-random number generator, and it was quite easy to break the security or to obtain the keys generated with this pseudo-random number generator. Another situation that I think Massimo Caccia referred to in the initial talk of the hackathon was this affair that happened when the NSA allegedly tried to introduce a backdoor in one of the pseudo-random number generators that was going to be established as a standard by NIST. This has not been confirmed publicly, but there were rumors, and in fact, the New York Times published that this was the case, that a backdoor was trying to be inserted in this generator, and in fact, NIST withdrew this proposal just shortly after. Also, it was mentioned this morning by Marco Macchetti, the case with the PlayStation 3, in which the pseudo-random number generator was just a constant. It was always the same number, and this led to a group of hackers to obtain the private key of the that was being used by Sony to sign all the software and to be able to pirate the games. So these are just examples of things that can go wrong with your pseudo-random number generator. And then maybe you are now considering, well, what is the alternative? What can I do if it is so difficult to find a good pseudo-random number generator, or if you can have problems with the implementation or with the seeds? Well, I don't want to correct Albert Einstein, the great Albert Einstein, but he was wrong when he said that God does not play dice with the universe. We know that quantum theory is essentially random, and this is something that we can use to our benefit when we try to generate randomness, because we have at our disposal random processes that are completely random if quantum theory is correct. In fact, this has been experimentally tested via this CHSH game. I don't want to go into much detail because I think I'm already over time. But the idea is that you can set this game in which you have Alice and Bob that are very far away, so they cannot communicate, and you send them 2 bits, and they have to respond to these 2 bits that they receive. One receives A, and the one receives X, and the other one receives Y, and they have to respond with their own bits A and B, and they have to satisfy this relationship in the slide to win the game. And it is very easy to show that in a deterministic universe, they can only win with at most 75% probability, okay? So you can check all the different strategies, and they can also maybe set a strategy in advance to even they can share some randomness that they generate previously, but you can show that at most they can win with 75% probability. But if you allow them to use quantum resources, in particular, if they can share entangled pairs, Bell pairs, it can be shown that they can win with a probability which is about 85%. You just have to compute what are the different probabilities of measuring this state with different bases. It's not very difficult, and you show that the probability of winning this game with the use of entanglement is bigger than what you can expect if the universe is deterministic. And this has been experimentally verified first by Alan Aspect and his group back in the 80s, and more recently closing all possible loopholes or all possible problems with these experiments by Hansen and his group in 2005. So we can be certain that something random, something not deterministic is happening when we measure a quantum state. And this is something that we can use as random power, the people at Random Power know very well, to generate randomness for your applications without the problems that we have been mentioning so far. And just as a closing thought, this phrase from the great Donald Knuth that said that, well, if you want to generate random numbers, the method that you choose should be not chosen at random. Thank you very much for your attention. And well, if you have any question or comment.
Fantastic, very nice. Very nice, very clear, Elias. Congratulations. So do we have any question by the people in the audience? Yes, Arda, please go ahead.
So the microphone's not working, so I will do reading. How can we calculate the information that a physical system contains, and how can we decide an entropy source is high quality? After calculating the total entropy, how can we decide how many bits can we generate from that source? Well,
that is a very, very difficult question. This is very difficult because, well, first of all, to test the entropy of the system, you usually don't use this Shannon entropy, but you use the mean entropy, which is a different measure, which is related to Shannon entropy. But to compute this, you need to know the probability of each and every string, because this is related to the probability of the most likely string. And this is something that if you have a system that generates strings of, I don't know, 100 bits, it's impossible, because you need to know the probabilities of 2 to the 100 strings.
Any configuration.
It's impossible. So you need to resort to other kind of method. Either you analyze the system and you model the system, and from that up to a certain level of certainty, you can assure that the entropy you're obtaining is above a certain threshold, or you can use something similar to this CHSH game. In fact, this kind of game can be used to give a lower bound on the entropy of your system. Somehow this is a certification if you obtain what we call a violation of the Bell inequalities, in this case, a probability of winning which is above this 75%, then you have also a bound on the entropy of your source. It has to have at least some entropy, because otherwise it couldn't beat this 75% probability. And this is something that is used with this game or the GHZ game and other games in order to give lower bounds on the mean entropy of quantum random systems. And this is something that you can use together with randomness extractors, which are similar to the hash functions that Marco Macchetti was mentioning this morning. And if you meet certain criteria, then you know that you can amplify your randomness And starting from a weak source of randomness, a source of randomness, which has some entropy, but not much, you can increment this entropy. So this is a very nice, a very interesting field of study, which involves topics from computational complexity, from quantum computing, and from cryptography. And it can allow you in certain cases, like these quantum settings, to at least obtain a lower bound on the entropy of your system.
Elias, can I ask you a question?
Sure.
So what is your test bed? So while you are at the open lab, how are you going to test whether the random numbers that you use are actually high quality? I guess on a physical system, but as a particle physicist, I'm very much intrigued to learn what you're doing.
So, well, of course, we first run the classical test suits like NIST or Die Harder, these kind of suits. We also run some simple Monte Carlo simulations, for instance, to compute or to estimate pi. We use these Icing models because this is historically important, and we know that some pseudo-random number generators that were considered good at the time failed these tests. And we are also exploring the possibility, that's why I mentioned it also in one of the first slides, to use this to test the behavior of generative models and other machine learning models to see if they improve somehow the training process. But this is a work that we have not completed yet. We are working hard on this, and well, it's very interesting, but also very hard because, well, nowadays there are very good pseudo-random generators.
Oh yes, there are. Yeah, on Pi, you know, we'll also exchange some information. Pi is something very simple, but it's apparently providing you some information.
Sure.
And the other question is, in order to make sure, in order to be able to make a statement, how many bits do you usually need?
Oh, we need a lot. We need, it depends on how hard you want to test the system.
Sure.
But for instance,
it might be a never-ending story. I agree.
Yeah. But for instance, for these Icing models, if we increase the size of the lattice, we can need I don't know, 10 to the 15 bits or something like that. So
10 to the 15.
Yeah.
Okay. So 1 million gigabit. 1 million gigabit is a lot.
Yeah, on that order, to try to see some difference.
Wow.
Yeah, because, well, if you test against these bad pseudo-random number generators, you can see the difference.
Immediately, very clearly.
Not immediately,
not
but
immediately, but with a small sequence.
With less bits. But the pseudo-random number generators that are being used now can obtain the correct values even for big lattices. So it's difficult to beat them.
But then the other question is again related to that. If you see differences after, say, 10 to the 15 bits, then for the simulation that you're actually performing, it doesn't really make any difference, because could it be that you just stop before actually the non-randomness, or say the randomness violation pops up?
I'm not sure I understand the question.
So meaning, say that, for instance, you want to simulate a series of LSE events, or when I was actually there, a series of events at lab. They were much easier. Then it may well be that the statistics that you need is such that you don't get actually to the limit of 10 to the 15 bits. So you stop beforehand.
Yeah.
And then it looks like saying, maybe my physics channel has not actually the requirement or the sensitivity, which is such to go actually to the extreme.
Mm-hmm. Yeah, that's why we are working hard and talking to different departments at CERN to see what are the needs and what are the problems that are the most difficult for today's pseudo-random number generators, which are the problems that demand the highest quality randomness in order to obtain correct results. But well, this is also difficult because as you mentioned, there are problems in which you don't require so many bits, or you can stop earlier.
Thank you. Do we have any other question to Elias by the audience? Okay, if not, I really thank you again. It was very nice lecture.
Thank you very much.
If you don't mind actually sharing your slides with us, we will keep it for the record.
Pleasure.
We will make them available to the people who are competing and attending, because they really provide a very, very useful insight. And then let's keep in touch. I sent you already, say 30 to 40 gigabit for fun. And then if you need more, you just let me know.
Thank you very much.
Thank you.
And good luck to all the teams.
Thank you. Thank you, really. Very, very nice of you. Okay, so this is, we have also our, say, chat moment with the people. You can stay, Elias. You're most welcome to stay if you like. So how things are going, people? I see that we have nearly all of the people that are attending, all of the competitors, but the people in at the Georgia Tech, because they send me a message saying that they have a hurricane on the region, so they have other sort of problems at the moment, so they cannot connect. But they will be, although they continue working, and they will be again online tomorrow. So it was for me a very interesting day, honestly speaking. We had 3 speeches that were a very, very high level. They were tackling different aspects of randomness, and each of the speakers was actually bringing in something useful. So I don't know what is your point of view. For me, it was also an indication by the fact that we had a number of questions to the 3 speakers. That was really, really good to me. So anybody of you wants to comment? You're still alive, you're hyper tired, you're super stressed, or you're managing the competition in a smooth way?
Technically still alive.
Okay, good. Don't think that is much softer for us, honestly. So it's also very committing.
Yes.
Can I ask an unrelated question?
Sure.
If it's okay. So for the board that you have, the pocket-sized board, can it be compatible with other small, let's say, computers, so that you can recall the data at any point while it's in your pocket?
Yeah. Yes, it is. Meaning that as it is by now, you just plug it in through the USB and you run it. That's it. Okay. So you can do it essentially on any computer, honestly. We have a Python, we have Python libraries and C libraries to make everybody happy. So honestly, for the development, we are more on the Python side, on the Python side. So the continuous update is done on the Python libraries, but we have both. So, but it's quite handy, and it's actually what you saw in the picture. It's more than a credit card. You need a USB, and then you plug it in and you go.
And then you can use it whenever you want to decrypt and encrypt whenever you want.
Yes. Once you have the data stream, you can really do whatever you want.
That's amazing.
I mean, if you want to have one board, let me know after the event. So
okay,
we can try to make a deal. And we have special prices for you.
Thank you.
No, it's not a joke. This is applicable to most of the people. Of course, we have a limited production by now, and I don't want to exploit it. But if we do see that there are requests by other people, we can also launch a second production.
That's interesting, actually.
This is interesting.
Can you tell us maybe a bit more about prices of the boards?
Yes. I can tell you something. So of course, it's preliminary estimate, and is based on the cost to produce, let's say. And of course, the price that I'm going to tell you is very much related to quantity. So it's estimated on the positive assumption that we will get by the community a significant number of orders. In such a case, we can negotiate with the silicon producer a good price for the device that we're using. And then through the rest, we can negotiate a good price for the provider of the FPGA, because the core of what we do is essentially the generator in silicon and the FPGA to manage the system. But think positive, like most of the marketing people shall do, so it's not me, honestly. I'm at the opposite side, but I would say that a reasonable cost per unit is in the range of 500 to 700 euros, which is honestly half of the price of the IDQ single generator board that you get.
Yeah.
So it's
Jose, we have to convince Alberto, I think.
Okay. Yes.
Come on, it's almost Christmas. We can make a case.
It's almost Christmas, yes.
But it would be very interesting if we could, you know, make it so that we can put it in with a small computer, and then anytime we want the data to be encrypted, then we can just directly apply it.
Yeah. No, honestly, this is already possible. This is what I do every day. So when I need to qualify each of the board of the production, first I sit down in my lab, I define the startup values that are going to be hard-coded in the flash memory. And then once this is done and certified, you know, I'm essentially an analog guy, so I need a scope to make sure that I'm doing things properly. Then I start the production. And so wherever I am, I have in parallel, which is, say, getting my Mac a little bit hot, but I have it running. And then continuously I produce, I analyze my own simple zero-order test first. And if they are correct, then I go through the NIST. And if I do so, I can have about, say, working in background, I have 6 gigabits of data per day, which is not bad. Huh? It does it for you. So you have it running while you're doing something else.
Yeah, we actually thought that we're going to have the problem with the limit, because for simulation you need a very large amount of you know, random bits, but it's actually very quick. So we think that for the moment it's quite good for the simulation.
Fantastic.
Yeah.
Good.
What
and
about,
the idea would be, this is another possibility that we are considering, meaning that if we do see that you need a large amount of data, we can also imagine to set up a sort of randomness on request. So we fill in our reservoir running a battery of single boards. Then whenever you need, you click. And then you have your own reservoir and you download what we produce for you. But of course, I mean, it's just another way of distributing it. But I like the idea that you really have it with you, honestly. Huh?
Yeah.
That's
what you get with the random
number
is exactly what we do for this event. So this
yes,
is
exactly. Carlos is absolutely right. This is what we're doing for this event. We have a pool of 30, or I should say a pool which is about 30 to 40 gigabit, say, deep. And then we keep on filling it with the new ones. And we have one board which is running at the GlueNet premises.
Can I?
Of course, Jan.
Just, because that was more or less my next question. To propagate your technology, didn't you consider trying to somehow advertise and like random on-demand service?
Yeah. I mean, we can do it, but you know, honestly, I mean, it's now the victory that we had is triggering really a snowball effect, and so now I'm overwhelmed. So then I have to sit down quietly, starting end of next week, and just make a list. But you are absolutely right. I can tell you even more, because of course you can you want to download, and you're a researcher, you click and you get it upon request. But one of the problems that we realized by speaking to other companies is the fact that you want to make sure that the data are not say, corrupted on the way. And so there are series of randomness providers, for instance, for gambling, whose main concern is not so much randomness in itself, and I think they are wrong. It's the fact that they can qualify the fact that there was no eavesdropper or intruder on the way in between the generation and the receiver, which, if you think of it, when you're talking about, for instance, an online gambling system, of course, makes some sense. So this is a technology that we don't have, but we could imagine to partner with people that do have this system, or to profit from one of the proposals that I know you are developing in order to implement it properly. So
yes, I'm working to something similar for my proposal.
I know, Valerio. So this is why I'm triggered, because actually what you're doing is going absolutely in this direction. So this is a message to everybody. So you're competing, but for us, this is not the end of the story. This is possibly the beginning of the story. And if we manage by the end of the day to get something that you're developing embedded, of course, with a full recognition of what you're doing in our endeavor, then we will be happy. Yeah, what you're doing, Valerio, is very intriguing.
I have a question about using. Firstly, thank you very much for the speech of today. Thank you to Elias for the very interesting and nice speech. I have just this question about using these random numbers for simulations and their computation in general. If you require some kind of repeatability in for example, in a GN4 simulation. I suppose it can be a problem because you have to store all the true random generated numbers data on some disk. And so, or you can use the true random numbers, like, for example, a feeding for a PRNG. So you can, in some way, to amplify the quantity, but keeping writing only a small quantity of data. Otherwise, you need a lot of memory, not only a lot of computing hours. So what do you think about this problem? It can be a limit.
So, Elias, I let you start and I tell you my point of view.
Yes, of course you are right. And this is something that comes once and again when we talk to different people here at CERN. And they require, or one of the necessities they have is the possibility of repeating the same experiment. And of course, you have two choices, either to store all the values, which can be very expensive in this space, or as you have mentioned, this is another possibility. You can use these random, true random numbers as seeds, and that is a good possibility.
Yes, and I agree with Elias. And actually, if you look honestly also to the majority of the market system, and also the hardware security modules, now the majority of them is using this mixed mode working. So you use a TRNG, possibly a QTRNG, in order to seed the PRNG. So this is very much in fashion today. And you have nice systems. You can also look at the systems by, there's this one of the major HSM producer, Gemalto. The system by Gemalto, for instance, is working exactly this way.
And it's a good solution because you can combine these true random numbers. You have seen that if you don't see the pseudo-random number generators correctly, you can have problems. So you can make sure that your seed is good, it's truly random, and then you can use pseudo-random number generators that are not totally uniform, but are uniform conditionally on some computational complexity problem. For instance, you can design pseudo-random number generators that are really uniform, provided that the seed is truly random, unless P is equal to MP. Okay, and if P is equal to MP, then we have different problems. It's a different situation. But you can construct this kind of pseudo-random number generator and seed it with a true random number generator. For instance, there are different combinations that you can think of.
Can I ask something in this situation? So we know the simulations are supposed to be repeatable, but the thing is that real life events, so we're talking about high energy particles, rare events, they won't always be repeatable. So in a sense, you expect them to not be repeatable, to not act the same every time. So why is it very important for us to get only one result instead of getting, for example, a pool of results, possible results, and then just predicting one of them will come true?
Well, I don't know. I tell you by my own experience by the Delphi time. Because, for instance, I remember that there was a time when we were, for instance, say, upgrading our computer center. And then you just wanted actually to make sure that you did everything the right way. And so repeating simulations on the new cluster was actually a method for diagnostics, for diagnosing the fact that everything was properly done. And then you want to do it really in a deterministic way, but using a Monte Carlo simulation. And in such a case, you really want to repeat exactly the same series of events. So it's not, in our case, it was not so much for physics studies, it was for diagnostics whenever you were introducing a new machine or you were introducing a new, say, hardware or software or firmware. So you see, and this is one possibility. Then the other possibility, but again, it wouldn't apply if you have true random number generators, was the fact that you were running in parallel on the different processors of your system, and you wanted actually to make sure that you were not entering the loop in the same way. So then in such a case, you had to add a seed so that the end of one system was triggering the next in order to avoid looping the loop. So it's more, for us, say, by my limited experience, it was more a technicality that was required to certify the processing. So it had nothing to do with physics, essentially.
Yeah, and another use case is, well, related to what Massimo was mentioning, is to debug your software. Sometimes it's very, very difficult to debug, even when you have a deterministic algorithm. When you have a probabilistic algorithm, like a Monte Carlo simulation, it's even more difficult. And if you cannot somehow fix the source of randomness, maybe your bug only happens if a certain set of conditions are met, and then you cannot observe it again, and it's very difficult to debug. So if you can fix by inputting the same seed the source of randomness, debugging it's a little bit easier.
I agree.
Thank you.
Okay, do we have any other question? Then I have a question to all of you. Do you want actually the wrap up tomorrow morning, or do you want to keep going until noon, or say noon and then getting ready for the discussion and the presentation? Oh, just a second, somebody ringing me. Give me 3 seconds.
Meanwhile, I think I would like just to mention a few things. So I'll circulate a template document for you to fill in a bit about your project, what you do, a few deliverables you have, either repository or slides or whatever you want to share up to you. And you just basically would just to push for you know, anything you want to report on the project. Your slides are your slides for tomorrow, or no slides, up to you. It's something else. But just so we have a little overview in your own words of what you're trying to do, you know, like a brief summary, I think that would be much appreciated. Thanks.
How does that correlate with the project proposal with it? Because
so it's mostly like what we call this the one-pager. So you basically report in a page what you think would be the gist of what you did. So it's mostly like to ease reporting when, you know, we show what happened, and Massimo is basically to help him, basically that he doesn't have to go in all the details, because obviously you made a proposal and maybe all of you are exactly working on your proposal, but maybe you shifted a bit the idea since you started, because basically things have changed a little bit. Not much, the goal is the same, but what you did during the hackathon was, you know, a first step or a first area or something. So it's mostly something small.
Mostly this, I mean, if we haven't deviated too much, mostly the same than the proposal.
Yeah, exactly.
Both
I mean,
are one-pagers.
Right. Don't waste too much time on this. Don't spend too much time on it. It's really more to easy get an overview.
So tomorrow by 12, right?
Well, yeah, whenever you want, it's fine. Tomorrow by 12 is good. If it's a bit later, it's not for the presentation or anything. It's your presentation is really what matters.
Okay, good.
Cool. And I'll send you a template. It's gonna just a Google slide, Google document, sorry. And I'll also share a folder in which anything you want to upload, your slides or something, if you want, you can do. If not, we'll work on the principle that you share your screen tomorrow because it's the easiest thing to do. Do we want to wave goodbye to everyone that we're closing the webcast?
Sounds good to me.
The presentation is still in the same time, right? Not in the morning.
No, it is at 1.
Okay. Yeah. Yes.
That has, I mean, 1 Central European time.
Yes.
So see you tomorrow at 1?
I guess so, unless there's something else, but yeah.
Well, I hope from our friends in Georgia in the United States that they won't be in their hurricane anymore.
Hopefully, we'll hear soon enough, but yeah, it's always difficult when these things happen.
Yeah. So.
Take care. Bye-bye.
Ciao.
You too.